All right, let's talk about something that's kind of terrifying for any developer. We're going to explore that really thin, fragile line between cryptographic genius and just catastrophic failure. You know, how perfectly good math can be completely undone by these tiny, all too human mistakes in our code.
So that quote, it's describing Stuxnet. If you haven't heard of it, it's basically considered the world's first true digital weapon. But here's the crazy part, the thing that should keep us all up at night. Stuxnet didn't have to crack some super complex encryption. No, it went after something way more common, and honestly way more dangerous. Simple implementation errors, the kind of mistakes that developers like you and me might make any day.
Which leads us to this question. How can math, that is, for all intents and purposes, unbreakable, be defeated by just broken code? Seriously, think about that. Understanding the answer to this is absolutely key because it's at the heart of pretty much every major security breach you've ever heard about. So yeah, let's break it down.
Okay, so to really get a handle on this threat of bad implementation, we've got to look at the weapon that basically perfected exploiting it. We're going to deconstruct Stuxnet. All right, first up, zero-day exploits. Just think about it for a second. Imagine there's a flaw in a piece of software that nobody knows about, not even the company that made it. An attacker who finds that flaw has a key to a lock that no one even knows exists. Stuxnet didn't just have one of these secret keys. It had 4. That's like having a whole master set. Just an incredible show of force. So once it got inside, Stuxnet wasn't just some noisy virus. No, it was way smarter. It used a rootkit to just cloak itself, hiding deep inside the system's software. And what this meant was it could actually change what the system operators were seeing. It could feed them perfectly normal-looking data, while in the background, it was getting ready to do some real physical damage. It was literally a ghost in the machine.
And this, right here, was Stuxnet's ultimate target. It wasn't after data, it wasn't after money, it was after the physical world itself. These things, PLCs, they're the tough industrial computers that run everything. Power grids, factories, you name it. By going after the code on these devices, Stuxnet bridged that gap from a digital threat to actual physical destruction.
So when you put it all together, you see the whole brilliant, terrifying attack chain. This wasn't just one hack. It was a chain reaction, a whole series of exploits, and each and every link in that chain targeted a specific implementation failure. It started with a simple USB stick, and from there, it navigated a secure network, made itself invisible, and in the end, it manipulated heavy machinery until it literally tore itself apart. Okay, so you might be thinking, I'm not defending a nuclear facility. And you're probably right, but the attackers who are trying to break your applications, they are using the exact same mindset as the people who built Stuxnet. They're hunting for the exact same kinds of simple, everyday mistakes in the code that we all write. Let's look at a couple of examples. Okay, look at this. This is probably one of the most classic textbook implementation errors in the history of programming, the buffer overflow. See the function on the left, string copy? It just blindly copies whatever the user gives it. So what happens if the input is too big? It spills over in memory, and that spillage can overwrite critical parts of your program. An attacker can use that to take complete control. Now look at the safer version on the right. See that limit? That one tiny change is the difference between a secure program and just leaving the front door wide open. But here's where it gets even crazier. Attackers don't just look for bugs in your code's logic. Sometimes the weaknesses are in the actual physics of how your code runs. This is what's called a side channel attack. The idea here is that the very act of your computer processing data, the hum of the CPU, how long an operation takes, can actually leak the secrets you're trying so hard to protect. No, seriously, think about this. If your code takes just a tiny fraction of a millisecond longer to check a password that starts with the right letter versus a wrong one, an attacker can measure that and figure it out over time. If your chip draws a tiny bit more power when it's doing one specific cryptographic step, yep, that can be measured too. And this is why we as developers have to realize that secure code isn't just about good algorithms. It is a deep, deep engineering challenge that goes all the way down to the silicon. So, okay, this all sounds pretty bad. How do we defend against all this chaos? Well, it's not about finding some magic tool or a silver bullet. It's about fundamentally changing how we design our software and how we approach the whole process of building it in the first place. Here's a really powerful way to think about it. Look at the code on the left. We're accepting a generic string for a phone number. I mean, anything could be in that string, right? Total garbage. Now, look at the right. We're not asking for a string. We're demanding a phone number object. This little change is huge. It means the validation happens by design. It's literally impossible for an invalid phone number to even exist in this part of the system. We're making insecure states totally unrepresentable. It's a game changer. And this quote, it's from the world of surgery, but man, does it hit the nail on the head for us developers. Even the absolute best, most brilliant experts make simple mistakes, especially when things get complicated. We have the knowledge, we know how to build secure systems, but under pressure, we miss steps. And that is exactly why, just like pilots and surgeons, professional developers need to rely on robust processes. We need a checklist, not a piece of paper, but a systematic, automated approach baked right into your CI/CD pipeline. When you do that, security stops being this stressful thing you tack on at the end, and it becomes a repeatable, professional habit that catches those simple, devastating mistakes before they can do any harm. And that brings us to the final point. The single most powerful defense you have. It isn't a tool, it isn't a library, it isn't even a process. It's a change in your own mindset. It's about learning to see your own work through the eyes of an attacker.
And listen, this is not paranoia. This is just professional diligence. Every single line of code you write, every library you import, it all becomes part of your attack surface. You have to write your code, you have to review your code with the assumption that a determined, clever adversary is out there, right now, looking for that one small mistake that you might have made.
Which really leaves us with one final question to ask ourselves. Your code is out there in the wild. Who's testing its security more? You or them? Because in the world of software, you're either hunting for your own bugs or you're just leaving them there for someone else to find. And trust me, someone is always looking.